Welcome back. In one of our earlier classes, we have already learned about the laws of positive integral exponents. Now, in today's class, we will be learning about the laws of negative integral exponents, and we will see that whether the exponents are positive or negative, the laws will be same. As first law, what we learned was a to the power m multiplied by a to the power n was equal to a to the power m plus n, where a is the base and that is non-zero rational number. M and n both are exponents, and here m and n both are positive, that is greater than 0. Now in this case we are here learning the laws of negative exponents. So here we will be having three cases. Three cases means when m and n both the exponents will be negative, means less than 0. Second case is one of the exponents will be positive and the other one will be negative. Let's assume that m is positive and n is negative, and then m is negative and m is positive. And in all the cases we can prove that whether one exponent is negative or both the exponents are negative, this will follow the law which we learned in case of positive exponent also. Now we will prove first for the case 1 when m and n both the exponents are less than 0, are negative. So here m, since it is negative exponent, so let's assume m is equal to minus p and n is equal to minus q. Now again left hand side, if we put the new value of m and n, so on the left hand side it is a to the power n multiplied by a to the power n. Now it will be written as a to the power minus p in place of m minus p, and then a will be a to the power, it will be minus q. In place of n we will be putting minus q. So a to the power minus p, that means it has this format a to the power minus n, and it will be written as a divided by a to the power n. So it will be written as 1 divided by a to the power p, then multiplied by 1 divided by a to the power q. Now in the numerator we are multiplying both the ones, as we know the law of or the rule of multiplication of rational numbers. So 1 will be multiplied by 1, and in the denominator a to the power p will be multiplied by a to the power q. So in the numerator it will be 1, and in the denominator it will follow this rule that a to the power m, in the denominator both the exponents are now positive, so and both the bases are same, so it will follow this law. So we can write a to the power p plus q. Now it has the form 1 divided by a to the power n, so it can be written as a to the power minus p plus q. Minus p plus q, why it is minus p plus q? Because 1 divided by a to the power n is equal to a to the power minus n, so a to the power minus p plus q. Now if we separate these two exponents, then it can be written as minus p then minus q. So it is a to the power minus p and minus q, or we can arrange this way, minus p plus of minus q. So now if we put in place of minus pm that we assumed initially, and then in place of minus q if we put n, so finally again we are getting a to the power m plus n only. So whether the exponents are positive or negative, it will follow the same rule or the first rule that we learned already. Now this I have proved when both the exponents were negative. Now this can be proved for when one of the exponents is negative and the other one is positive. Let's proceed with the case 2 when m is positive and n is negative. So the law is a to the power m multiplied by a to the power n. For positive exponent it was a to the power m plus n. Now this time m is positive and n is negative, so in place of n let's assume n is equal to minus q. So left hand side, now if we rewrite, then it will be a to the power m, because m is positive, so we are not changing anything for m. Now in place of n we will be writing minus. Fine, then it will be a to the power n, and then it will be 1 divided by a to the power q. As we know, again I am writing that a to the power minus n will be equal to 1 divided by a to the power n. So this can be further written as a to the power m divided by a to the power q. So here what we can see is, now this can be thought or written this way: a to the power m and then 1 by a to the power q. So this can be again written as a to the power m, and 1 by a to the power n means a to the power minus n, this format. So it will be a to the power minus q. Now again both the bases are same, which is a, and so we will add both the exponents with their sign. So it will be a to the power m plus of minus q. Now since minus q we assumed was equal to n, so in place of minus q now we can put n. So it will be m plus n only. That means again we are satisfying this law. So even if one exponent is negative and the other one is positive, this law will be again satisfied. And this can be again proved for the third case, when n is negative and this will be n, and n will be positive. So the proceeding will be same, the calculation will be same. So here to prove this case 3, the process will be same. So I am not repeating the case 3, as we have already learned the process in case of case 2. Now we will move on to the second law. Second law, what it says is, if suppose if we are dividing this a to the power m, when we will divide by a to the power n, then it will be a to the power m minus n. And this is true for positive integral exponent that we have already seen, we have already learned. And now this time we will be proving this for negative exponent as well, that this holds true for negative exponents. So again for this law also we will have 3 cases, and I will explain only case 1, and you can easily prove case 2 and case 3 if you go by the same process. So for case 1, what it is, when m and n both the exponents are negative, less than 0. So again we will be going by the same process that we have seen for the first law. So we will assume m is equal to minus p and n is equal to minus q. Now let's proceed with the left hand side. So left hand side, on the left hand side we have a to the power m divided by a to the power n. So it will be a to the power minus p, then divided by a to the power minus q. Now since both the bases have negative exponents, so first one will be expressed as a to the power 1 by a to the power p, then divided by 1 by a to the power q. Now 1 by a to the power p, and since dividing we are, so we will multiply by the multiplicative inverse of the second number. So it will be a to the power q. Now in this line we have both the exponents positive, p and q. So it is a to the power q divided by a to the power p. So it is following the second rule. So as per that rule we can write a to the power q minus p. This q and p both are positive here, so we can follow the rule, the second rule that we have learned for the positive exponent, and as per that rule it is a to the power q minus p. Now here a to the power q is what? N is equal to minus q, so q will be equal to minus n. So in place of q we can write minus n, then minus p, and p is what? P is minus m. Here it will be p will be equal to minus m, so it will be a to the power minus n, and then minus minus it will be plus. That means finally it will be a to the power m minus n. So that's what we have obtained in case of positive integral exponent. So whether it is positive exponent or negative exponent, the second rule will be also followed. So second rule will be also same for both the cases. Now we will go to the third rule. Third rule, what we learned in case of positive exponent. Third rule says that if it is a to the power m, where a is base non-zero rational number, m is positive exponent, and that result if we make base and if we take exponent of that, and that exponent is n, a different exponent, then it will be equal to a to the power m multiplied by n, or we can say a to the power n multiplied by m. Now again it will have three cases that we have already learned in rule number 1 and 2. So I am not writing all these cases. I will prove the first case when m and n both are negative, and you can by yourself easily prove the second case and third case if you understand the first one. Now the left hand side, it has this value a to the power m and then to the power n. Now we have assumed that m and n both are negative. So m, if we assume, is as minus p and n as minus q, then we will replace both m and n. So it will be minus p then to the power minus q. So we will start processing from the outside. So it is altogether, it will be taken as a rational number, non-zero rational number, and as a base, and to that base this is the power. So it will be 1 divided by that base to the power positive exponent, right? So this is the whole base, then a to the power minus n will be 1 divided by a to the power n. So now what we will do, it will be 1 divided by, then we will write 1 divided by a to the power p then to the power q. Now this can be further written as 1 to the power q divided by a to the power p to the power q. So this now can be further written as 1 divided by, now 1 to the power q means 1 is getting multiplied by itself, means 1 q times. So it will be 1 only. So in the denominator it will be 1 divided by a to the power, it will follow this law, it will obey this law. Here p and q both are positive exponents, so it will be a to the power pq. Now this will be 1, we are dividing by 1 divided by a to the power pq, so it will be 1 multiplied by a to the power pq, multiplicative inverse of the second number. Okay, so it will be finally a to the power pq. Now we will replace p and q in terms of m and n. So it will be, in place of p it will be minus m, as m is equal to minus p, so p will be equal to minus m. Now minus m will be multiplied by minus n, so it will be finally a to the power minus minus, it will be plus, so a to the power mn only. So whatever we saw in case of positive exponent, the same result we are getting for the negative exponent as well. Now I have proved for the first case. You can easily by yourself try and prove the second and third case. So I am not repeating the second and third case. Now the fourth law. So what was the fourth law? In fourth law we had two different bases and same exponent, and if it is ab to the power n, then it will be equal to a to the power n multiplied by b to the power n. Now since here we have only one exponent and that exponent, so here we will be having only one case, and that there we will be assuming that the exponent is negative. So n is negative, so we will assume that n is equal to say minus p. Now we will replace in the left hand side that n, the negative exponent, so it will be ab to the power n, means it will be written as, or can be written as, ab to the power minus. Now minus p means it will be written as 1 divided by ab to the power p. So now in the denominator the exponent is positive, so easily it will obey this rule. So it can be further written as a to the power p multiplied by b to the power p. It will obey this law because in the denominator the exponent is positive. So it can be further written as 1 divided by a to the power p multiplied by 1 divided by b to the power p. So now it can be further written as, in terms of negative exponent, it will be a to the power minus p multiplied by b to the power minus. So further it can be written as a to the power n as minus p is equal to n, then multiplied by b to the power n. Hence this is also proved for negative integral exponent. Now the next law that we learned in case of positive exponent was that a divided by b to the power n it was equal to a to the power n divided by b to the power n. Now again here the exponent is same, it has single exponent, so here we'll have only one case, and n we will again assume as negative, so n will be taken as minus p. Now on the left hand side, if we replace n by minus p, then it will be a divided by b to the power n, so it will be a, it can be written as a divided by b to the power minus p. Now this can be written as a to the power minus p divided by a b to the power minus p. So a to the power minus p means we can write a to the power minus n, so 1 by a to the power n, so we can write 1 divided by a to the power p, and then in the denominator we have, and that is divided by b to the power minus p, so that can be again written as b to the power p. So further it can be written as 1 divided by a to the power p and then multiplied by b to the power p. So it is b to the power p divided by a to the power p. Now b to the power p means b to the power minus n and a to the power minus n. If we replace p by minus n, because n is minus p, so p will be equal to minus n. Now b to the power minus n means it can be further written as 1 by b to the power n, and then divided by a to the power minus n means 1 divided by a to the power n. So it will be further 1 divided by b to the power n and then multiplied by a to the power n. So finally it will be a to the power n divided by b to the power n only. And that's what we have also seen in case of positive integral exponent. Now the next law says that a divided by b to the power minus n, that will be equal to b divided by a to the power n, and this is also one important property which saves time if we know this rule. Otherwise in exam we have to always find this value. Now again we have one exponent which is negative, so let's assume n is equal to minus p. Now left hand side what it says, what it has is a divided by b to the power minus n. Fine, then it can be written as a divided by b to the power p. Since we know a to the power minus n is equal to 1 divided by a to the power n, so on the other hand we can say a to the power n will be 1 divided by a to the power minus n. So this a by b to the power p can be further written as 1 divided by a by b to the power minus p. Now this can be further written as 1 divided by a to the power minus p divided by b to the power minus p. So this will be nothing but 1 multiplied by the multiplicative inverse of the second rational number that we have in the denominator. So it will be b to the power minus p divided by a to the power minus. Now it can be further written as b by a to the power minus p, and what is minus p in terms of n? N is equal to minus p, so we can write b divided by a to the power n. So this is an important property or law which saves time if we know. So in today's class we have learned about the laws of negative integral exponents, and in next class we will be solving various miscellaneous exercises based on negative integral exponent. So I hope you have enjoyed the class. Thank you.